So now we're going to have a conservation of momentum problem where we start out, again, we're going to fire a projectile with some angle theta. And so if it just, if all we did was fire it, it would go and it would land, and we know that it would travel some distance r. And we already saw that that r is going to be v0 squared sine theta cosine theta twice that divided by g. Okay, but now let's add a complication. Let's say when we get to the top here, let's say that the thing that we fired is going to explode into two pieces. We're going to have one move to the right and we know that its final velocity is going to be 3 times v0x. And then the other is going to move to the left with some unknown velocity. Okay? And then the question is going to be, where do they land? All right? So now what we're trying to do, so now we've got an additional complication, right? First, it starts out as a projectile problem. Then we have an explosion. And then we have to combine this projectile problem with the conservation of momentum problem. Okay, so let's see how we would put that all together. Well, so the first thing we need to do is we need to find out what the velocity of the second particle is after the collision. Okay, so we know. So, and again, we're going to say that they split into two equal parts. So we know that the mass times v0x, which is m v0 cosine theta, is going to equal m over 2 v0x times 3 plus, we'll call it v2 times m over 2. So we can cancel the factor of m because that's in all of them. So we see that v2 is equal to v0 cosine theta minus 3 over 2. So v0 cosine theta. This is over 2, so it's 1 minus 3 over 2, which is minus a half times 2. So this is minus v0 cosine theta. So in other words, the velocity here is minus v0x. So once we found that, now we need to find where this explosion is taking place, because it's from here that we're going to find out where they land. Okay. So again, we know that r is 2v0 squared sine theta cosine theta over g, and we know that this distance is just r over 2. So this is just going to be v0 squared cosine theta sine theta over g. Okay, but let's just say we didn't know that, just for the sake of having to work out a little bit more of the problem. So again, what we can do here is we know that at that point we know that vy equals 0, which is v0 sine theta minus gt. So t is v0 sine theta over g. And so then we can plug that into our equation. We know that x, and we'll call this point x0, which is r over 2. So x0 is going to be 0. So just v0 cosine theta times t, which is, again, v0 squared cosine theta sine theta over g, which is exactly the answer that we already said it was going to be. Okay, so now we'll look at the two different particles. So now we'll look at mass 1, which we'll call the blue particle traveling to the left. Okay, so we know that x1 is going to be x0 plus 3v0x times t, which is v0 squared sine theta cosine theta over g plus 3 v0 xt, which is v0 squared sine theta cosine theta over g, or in other words, 4 v0 squared sine theta cosine theta over g. And we know that this is just 2 times r. So that tells us that mass 1 is going to land way over here. So now we're going to look at mass 2. Okay, and there's really 2 ways to solve this. And so we'll look at both of them. So the first way is just to solve it exactly the way we did for the first one. To say x2 is equal to x0 minus v0 xt, which is equal to v0 squared sine theta cosine theta over g minus v0 squared sine theta cosine theta over g, which is just equal to 0. So we see that the second one is just going to come back here, and it's going to land right where it started. Okay, so in other words, it's going to come back and hit us. So by shooting this firecracker or whatever off, this is showing you how you can get something that'll come, right back towards you. Okay, the second way we can solve the problem is by looking at the conservation. Is by looking at the center of mass, because the center of mass, okay, is going to follow this original trajectory the entire way. So the entire time, if you were to plot this out and calculate this for the entire time, the center of mass would still follow the trajectory as if the two particles had never split, right? So you may have to go back to Unit 4 to take a look to recall why this happens. But this is actually true. So even in something like this, where we're in a gravitational frame, the center of mass is still going to be at the center. It's still going to follow the same path as if the particle had never split. So that means that at the end, the center of mass is going to be located at r. Okay, so that tells us that the center of mass is equal to r, which is equal to x2 times m over 2 plus x1, plus x, well, it is plus x1, but in this case x1, we can just say is 2r m over 2 all divided by m. So again, the m's cancel out, and so we can just so we can move this 2r, these 2's cancel out, so we have an r, so we subtract that from the other side, and so we see that x2 again is still equal to 0. So there's 2 different ways we could do it. We could have done it by plugging it back into the equations of motion, but we also check now by making sure that that the center of mass still lands in the middle, and it does. So so I think this is a good place to end projectile motion. We'll have one more problem where we have now a 2-particle system, and they'll come together to the same place. But you see how now, all we're really doing is building on concepts we had before. We really haven't done anything new in this entire unit. All we're doing is really just kind of adding some additional algebra to the same types of problems that you were solving, for the last 6 weeks.